talking about some of the things that that we get involved in with the mainline type projects. Some of the details that we wanted on surveying and the importance of being able to go out and take a look, at least having somebody to check the survey, make sure that what we find. That was kind of the drift of the first part. Now we want to try to get into a few other items and some particular things, and talk a little bit about some track alignment things. But you know, one thing that you get in the main lines that you don't, as far as alignment and curves and stuff, is spirals and super elevation and things. We'll try to spend a little bit of time on that towards the end of the discussion here. But one of the things that, you know, one of the first things, if we're going to have a capacity type project, we're going to add another siding to the main line. One of the first things that you have to do is, what is the alignment of the new siding? And we go out there and get a survey. And what I've tried to depict here on the slide that's up on the screen is that you've got an existing track. I've over-exaggerated this, but you're going to go out there every 100 feet or so on the tangent, and you're going to get survey shots. And in some, you know, well-maintained tracks, the tracks are going to be pretty straight, you know, in the tangents and uniform around the curves. What happens is that if it's not maintained very well, or it hasn't been, you know, surfaced and lined recently, that you know, you're going to get some alignment changes because of gauge, because the way they're going to measure the center line of track is they're generally going to take one rail and measure 2.35, you know, a half gauge. Gauge is 4 foot 8.5 inches, or about 4.7 feet, and 2.35 is generally the standard gauge. So that they'll pick the north rail and the gauge side and try to set that as the center line, 2.35 off the gauge side, and that's the center line of track. So you're going to have some discrepancies because the gauge is going to get a little wider in, you know, in certain areas. So you might not be exactly in the center. The alignment gets off for, you know, a lot of different reasons. But anyway, so the point is that you're going to get these points that are periodically, you might stay on the one side for a couple and go back and forth. So when you're asked to have a new track that's at 15-foot or 20-foot track centers, you know, how do you go establishing that? And that's something you want to find out. Again, one of the things we stressed last time was talking to make sure that you understand what each railroad wants. I think this is a real critical thing, because it does show that the alignment probably isn't really exact currently. So how do you do 15 foot? So one option is we want, you know, nothing, you know, you want to maybe do a best fit line between the survey points, and then you can offset 15 feet, and then this line here will become the new alignment. Another way to do it is the railroad says that we want a minimum of 15-foot track centers. So you take all that same line that you had, and then you go and set a line, you know, try to do as straight a line as you could, and coming through the, you know, where it would, you know, be tight, and or put that line, you know, that tangent line on the furthest, you know, the alignment that will minimize your distance. So you put this off 15-foot offset. You know, that's another way. That's the one I prefer, because the railroad wants a 15-foot minimum. We don't know if they'll ever surface this track in the future. If they do, and they don't put it right exactly there, you could end up with points that are less than 15 feet. If you follow this, if sometime in the future they go line it, and, you know, okay, now you're perfect. But now you got something 14 foot, you know, 11 inches, 14 foot, you know, maybe, you know, I've seen it to where it's actually been as far off as as 3 feet, that's one of the worst case scenarios, but, having 6 inches off is not significant. So, if you follow this first alignment, you might end up with some existing track as being 14.5 feet, and that might be less than what you want. If it's 1.5 feet, you end up with 13.5 foot track centers, and now you're not even meeting the FRA requirements. So you want to make sure that you have that. So that's why I kind of prefer this one. Again, checking the railroad. The UP, my understanding is the way they want it, and a lot of times the way that people out in the field will be thinking it is it's 15-foot offset. The main line is straight, obviously, even if it's mathematically not. And then you just want to have offset that track 15 feet. It's easy for them to locate where that track is because they just measure 15 feet off of the existing main. My problem is that doesn't give you that doesn't give you a simple mathematical equation for that line, where this one does. This is an actual straight line that's on the computer, so it's easy to measure from and whatnot. This one isn't, but you want to make sure that you understand what the railroad is requiring and figure that out internally. And then once you decided which way you're going to do that, then everything else will follow with that. 15-foot centers, where the clearance point is. That's how you will measure that. One of the other things, identifying the capacity. We've done we did that original or our initial track alignment, and some of the things, some of the railroads, and this happened to be a CSX plan, they asked us to what they called a clear length diagram, which gave the capacity for that siding. They're shooting for, in this case, they were asking for 10,000-foot siding, and we'll come into a few reasons why we didn't do that. So that was their first thing. They wanted 10,000-foot siding, and so that's what you try to give them. Some of the things that they wanted to do was, where is that they wanted to place this signal, and they had certain criteria where you could start with a point of switch. They want the one signal that's going to protect coming in this way from this direction. They're going to want a signal is going to happen to be 58 feet or 50 feet ahead of the point of switch. At 15-foot track centers, they want the signal to not be any closer than 480 feet from the point of switch, and that's going to vary depending on what kind of curvature and things that you have. We'll take a look at the other end. It came up with a little different answer, but that was one of the criteria. So this one, because there was a curve in here, you can't see that in this diagram, but there was a curve in here. That's where they wanted this signal, but the train could not, if it's coming in this way and comes through the siding, it has to stop 200 feet short of that crossing, or they're blocking that grade crossing. So the clearance is measured from that 200 feet. Same way on this side, they came up with where the signal location is, but the important thing was 200 feet from that crossing. So the actual clear length of that stretch of railroad is going to, or that new siding that we're building, these other crossings or farm crossings, so they didn't count as far as blocking the crossing. So the capacity was 9,462 feet. So on first blush, that's, well, they asked for 10,000 feet, so why did we end up with that? One is we had to build a lot of track around the corner, already, because they couldn't see this signal, is one of the issues. And the other one, but it's in a curve. They can't put this turnout in the curve. We talked about that before. So it ended up being outside the curve, and you had to build a lot of extra track to get there, so that cost money. On this line was a branch line, not one of their main lines. So even though their standard is 10,000, what they came up with is we're okay with 9,400 Pete, oops. If somebody's not talking, we may want to put everybody else on mute. Something's breaking up here. So there are some of the things that you want to take a look at. You want to find out where the signal is, where you can measure the clearance point to, and generally speaking at 200 feet from a crossing, on CSX. The BNSF, for instance, in Illinois, they want to have that 500 feet from the crossing, because one of the rules in Illinois is that you want to have the crossing cleared 500, or the rule says 250 feet clear of the crossing. It can't have any obstructions in that quadrant. But the state of Illinois has asked for that be 500 feet, just to make sure that for crossing safety. So they added this 500 feet. So if this was in Illinois, this happens to be in Indiana, we followed the CSX plan of being 200 feet away. If this clearance was in Illinois, we would have taken another 300 feet off of each end and ended up with a little less than 8,800 feet. So we want to understand what those rules are, and you do a diagram like this to try to show everybody how that was calculated. In the case that we were talking about, they weren't ever going to run trains on that branch line. They didn't anticipate running any trains on that branch line that were going to be any longer than 6,800 feet, so 9,400 feet was plenty long enough. They didn't anticipate even if they detoured something, might get 9,000 feet, so they'd be okay. And if they wanted to have more, you'd have to do something with one of these crossings, either close the crossing, or divert it around. You'd have to take this one and go around the outside of this, and that costs a lot of money. So what we want to end up doing is understanding what you're needing, and then what are the costs to get that. So just kind of review what is the capacity required? What are the lengths of the planned trains? That's something that you want to ask. You might get a standard. We want sidings to be 10,000 feet, but we also want to understand what is the likelihood of getting 10,000-foot trains. To understand, one of the other situations that you might end up is where you wanted the siding. You might, get 10,000 feet, and we might have to go across a bridge. Well, if we don't really need 10,000 and we can get by with 9,500, it may be beneficial to stop short. So you want to take a look and see what are the planned length trains. You want to look at the impacts of the grade crossings. Them seem to be the thing that controls. You don't want to, have the train parked on the siding, because that's going to be an obscure vision for a passing train. You look down there, the train that you see isn't moving, but you forget the one that's on the main line is going through there at 70 miles an hour, so you think you're going to go around the gate because you think that, obviously they shouldn't be doing, but people start thinking that, well, that train is activating the gates, it's on the siding, and he ain't moving, I can get around this, and then they go around the gates and get hit by the mainline train. So that's important. Impacts of the sight lines to the signals. It wasn't real clear on that drawing, but because of the curve went around the corner, and you had to be able to make sure that you can see that. So sometimes the signal has to get moved to make sure that you can see the signal from the oncoming train. And then you want to meet the, making sure that you meet the expectations, but always qualify that with the extra cost, because sometimes having a 10,000-foot siding is necessary. If they have to pay, $800,000 to install a new bridge, that might be necessary. Or one of the things you might do is go look for another alternative. But in a case like ours, well, the likelihood of the trains are going to be shorter than their 10,000-foot standard. No reason to spend that extra money. So as long as you know under that stuff, you don't buy extra property that you didn't need. You don't have to make grade crossing that were unnecessary, or road changes. So you want to understand that. So will a shorter length? You want to be able to ask that question and be able to understand that right from the beginning. Some of the other concerns, the railroad wants to have access to the right-of-way to get to their signals, to get to their tracks for maintenance purposes. But out in the country, a lot of times they don't worry about people, trespassers as much. Here in a urban setting, they actually wanted us to put an extra gate in here. They wanted the good access, but then they wanted to be able to prevent people from going out on the track, unsecured, because they don't want people, trespassing just from a safety standpoint, let alone the vandalism potential and the homeland security type issues. Since the railroads are one of them items that it is potentially vulnerable. Now we want to take a look at existing, trying to handle existing water. A lot of times when you out in the country, you don't have quite as many impediments, but you might have different ones. This used to be a farm field, so there's all kinds of drain tiles. There was a ditch that kind of went across through here and went on to the other side, right through here, and kind of went this way. But this is going to end up being a 40-foot cut. We kind of looked at that last week. So we had to get the water that was coming from over here heading this way through that. So that what they did was upstream here, they intercepted the stream, brought it over, and channeled the water over on the other side, so it's at the same elevation. Went underneath the new bridge or the new roadway extension, and connected back into the bridge. It sounds good. The other thing you might have, and we'll take a look at that, is drain tiles that are being cut off that are draining the farmer's field, and how are they going to be accommodated? One of the things there, we're kind of showing the water coming off, well, back to, one of the other things was they had this pond here, or detention area, that had to drain. It used to drain across this way into this ditch over here. We couldn't do that anymore. We didn't want the water to fall just generally over the side and erode that. So what we did was, it's a semi-pond, but a detention area, and brought the water through on this side, which we see on this side, bringing the water from that upland area here. But because the soils were such that we had to take a look at what kind of erosion protection you were going to need to handle that water. Eventually, you had to, and you can see this is before it's all finished, but you can see that there's a lot of excess, from the erosion, sedimentation. One of the standard track ditches on the BNSF and the UP is a 10-foot, excuse me, a 10-foot bottom ditch. And the reason for that is to handle the sediment. So sometimes the size of the ditch is to handle being able to control the sediment. Other times it's going to be waterfalls. So sometimes you have to determine which one is more critical in that situation. So here's the end result. You ended up with areas that were we had some sand seams, but a lot of these is where the drain tiles were going into some ditch. We had to take that water now and down the side of the embankment. So wherever them under drains that were draining the farmer's field, we were cutting them off because of this big cut. We had to get that water down into the track ditch and down the hill. One of the other things that same project, it ended up that it has to go underneath another railroad that's way down in here. So we had to control the water that we were intercepting, that were coming down the hill, and put in ponds to try to limit the outlet, so we didn't have to resize the pipes underneath the adjacent railroad. It was also a floodplain area, so we had to be able, because we were putting fill in there, we had to have some compensatory storage as well. So you're trying to look at all them drainage impact the alignment that you come up with, and the grading plan that you're going to have to produce for that track. Here's just an aerial. So you had the water coming down, you had some ponds, there's a bigger pond over here, so you took all the track ditch. This was a 1% grade, so the water came down here fairly at a rapid pace, and then was able to go in these detention ponds. These detention ponds were cascaded because, one, it was still on that 1% grade, and it was in rock, so trying to minimize the amount of rock excavation to get your pond. And then the water was outlet, went through the track, and then it went through the other railroad's main line and out into the river. So that drainage thing on the main line, that's one of the major things. So that's where you often hear an H&H study is being done. So the hydraulic analysis, one of the things that the UP is doing on a lot of their lines is they'll do that study, and because of the changing in the use of the land use, most of their culverts now are way undersized for what the runoff is from those areas. So in a lot of cases, they'll add, jack and bore a bigger pipe. It's when they do a capacity project by adding a siding or a second main, they'll do the H&H study and determine that they need to expand or extend the culvert, but then also expand the waterway opening, and that usually includes jack and bore and another culvert. They'll also look at, there's cases where they have a single, currently have one where it's a short single span bridge. They would prefer to have culverts instead of bridges. They're easier to maintain and less obstructive for the railroad. So they'll put a pipe in the single span bridge, size that appropriately, but then add adjacent pipes to accommodate that. But so on mainline stuff, they're getting that H&H study and understanding, it may not be as simple as just extending that culvert. A lot of the smaller ones, but the larger openings, you have to take a real special look at that, especially when there's a stream or a bridge involved. And there's a case where, where there's the river, so we were trying to get all that outlet, through here and get out. The other side was outlet in here, went through a box culvert into something here, but we had to control the outlet from up here to make sure that we didn't have to, do anything more on the other railroad. It was easy to construct the box culvert here because this was a brand new track, but trying to get an open waterway and extra permitting, we try to minimize that. Kind of step into signals. Another thing that needs to be addressed up front, early coordination. You want to identify the sight distances, making sure that you can see it coming around curves. It's one of the things that the railroad signal guys are looking at. Where's that location? Where are you going to put that signal? Signal spacing. One of the things that you want to, I think we've talked a little bit about, they have block signals, so that they're like about 3 miles apart or something. You'll have a signal, maybe it's a little bit more, it depends on the situation. They might be up to, 5 or 6 miles apart, maybe even as wide as long as 10. But what that does is when you get a train in there, the signals are in red on both directions, indicating that there's a train in that block. So when you start doing something and adding track into something, the trains have to be able to stop short of that new signal that you put in there. So sometimes you have to space off. So a lot of times, even though your construction package is confined to a certain 2-mile stretch, you might have to do some signal work that might be 2 or 3 miles away, just because of stopping distance that you have to incorporate. Generally, we don't get involved in that, but that's something that when we were talking about before is the track charts. You get an idea of where the signals are, where other control points are, where other switches are, where other sidings are, and you get some kind of an idea. So that needs to be something that's going to have to be addressed. But the important thing is to getting that coordinated with the signal guys as early as possible. Ask for a designer sketches, making sure that our stationing, we're going to take a look at one in a second here, but look at, is our stationing the same as the signal guys are using? So making sure that we understand what that stationing is, and it's based on something that the signal guides have as well. One of the things we'll talk about it later, but clearance for the signals. Here's a situation where you had multiple tracks. You couldn't get in there, so you end up with a signal bridge. Here's you're going to have so when a train's coming out of this siding, it needs to have a signal. They turn the signals around here so the train isn't, because it's not in service yet. But the signal generally wants to be on the right-hand side. There's going to be another one right here that they haven't installed yet, but there was, this was only needed to be 15-foot track centers or 20, but I think we made it about 30 so they could put the signal in there, so it was nice and easy that the signal would be, on the right side where the trainman would expect it to be. I don't know if any of you have seen this is a designer sketch. They'll call it, signal schematic. There's a few other names for it. I lost my picture again. But it tells you a lot of things. Here, this happens to be one of the, same way, I think it was at South Rob, but the important thing is there's great, here's a ditch, so there's a bridge located there, so it kind of identifies where that is. Here's signals. It'll give you the railroad stationing, where that signal is. It'll tell you where the signal new bungalow that they want to install. It'll tell you where the signals are going to be placed. So you can identify where those are. They usually want to be able to drive there, so wherever that grade crossing is, they'll identify that. So there's a grade crossing here, so they're going to want to be able to drive down to this bungalow for doing their maintenance. So when you're deciding how wide this bridge has to be, you need to be able to determine, can I get the signal maintainer down to that signal equipment. So you want to make sure that you can have access. But there's a lot of information. Now, at this point, we were proposing to close that. It ended up not, they decided not to close it, so a few things changed. But the important thing is to try to identify that. That's where we started with. You didn't need a lot of this information, but we still needed to get down to that. Even if if this road was going to be closed, you'd have access to get down to it. So you always, even though it wasn't going to cross, actually cross the mains, you still had to make sure that it was still viable to get, to the signal equipment. This is a little bit more complex conceptual schematic. This is what the BNSF, I think they got a few different colors. This one was done for somebody else prior to following their current standards. But it identifies where new switches are going to be, new signals are going to be, future tracks are the green ones. So everybody understands and gets a good understanding of where the new track is going to be. And this is something that the railroad has sign off, so everybody knows what they're agreeing to and can proceed based on, the design can be based on everybody's understanding. A lot of times it'll identify clear links, like on this case. I think they got a better example here coming up. Here's a situation where, again, it was, pretty complex, but, we were trying that one where that grade was, where we were talking about the drainage. This happens to be that track going up to the UP. This happens to be the main BNSF main line. So they want to know where all the signals were, where they could hold trains. There's a lot of different crossover here, so they wanted to make sure that they knew how they could operate through this area. What this did was give them places where they could store trains, measure into different clearance points, not a whole lot different than we had that clear link diagram. In this situation, they weren't worrying about the 200 feet from the signals. They wanted to know what it was between signals, and they'll figure out by their rules what they have, or what capacity of train they could. Physically, they could put, a certain amount of length of train in there. So you have to ask, get an understanding from them of what information they want to install or have you place on the diagram. tries to help a little bit see some of the numbers. But here's a case from between this signal and that signal. We can put in a 9,200-foot train there. You know, between this signal and the signal for that switch, we could park. So they could actually park an 8,500-foot train in there. And if there was a train parked there, they could actually get around several ways. They could, if they're on this main, they could come across here and go around this way. They could go down the controlled siding and go all the way around. So it provided the operating department a good understanding of how they're going to get trains into here. They knew that, for instance, they could, get 6,000-foot train, in this location. But if they did that, they would be blocking this. It would also told them that these trains that are coming off from the UP would have to stop at this signal, and before they could start crossing over, they'd have 6,000 feet to cross over to get to the other main. Usually, even though that they have the ability with the type of signal system, it's signaled in both directions, but they still try to run things right-handed when they can. But a train would come off of here, go through this crossover and that crossover, and get down on this main line. So there's different interlockings, and the placement of the signals are an extremely important aspect of. You're going to start with a schematic like this, with a designer sketch, and try to come up with, and address the issues that the railroad is wanting you to accommodate. Some of the other preliminary things, just to get an idea, here's a situation where we put, they wanted several tracks. They built a new main and turned into, these are existing mains that had 83 feet apart, as we're showing here. What they want to do is put a new main over here at 15-foot centers and try to get some big long sidings here. So to try to get approval, how are you going to try to drain that situation? And what we did, here's a low point. We had some inlets periodically into a storm sewer in this location. But what we're trying to do is, where's the proposed tracks? One of the things here that varies between 15 and 16 feet. We set this like in that first slide where this was going to be. We went 15 feet from the minimum point, so it varied between 15 and 16, and then all the rest of them were 15, just like the half. These were designed so it was actually 22 always in between there. But you're identifying try to identify all the critical things that you have, and so the railroad can make a decision. So one, you can see what the issues are to resolve, and then the railroad will be able to easily understand what you had in mind. Here's another one, just taking that a similar thing, access roads. Access road, I'm going to need property. We're going to have to extend some of these culverts. We're going to have to get into that property acquisition, so that was property that we're going to need to assess. We're going to identify, all the pertinence. You're going to put mileposts. The railroad always wants to know what mileposts you're at. You want to identify what mileposts that the new switches are going to be at. Again, here, the culvert ends up being extended not only long enough to handle the siding, but also the access road to get down there. And they were the kind of things, if it got to be too expensive, they can always get there by rail. But signal guys, it's in the middle of the night, it's an emergency. Usually their signals are going to go out, during a storm or something like that. So not only is it at night, it's in a storm, it might be raining. The truck, the guys don't want to have to be walking from a grade crossing that's way down here. They want to be able to drive to and they want to have generally an all-weather type road, so they want to have it good enough that, so it's going to be made of crushed stone, access to wherever they want to get. Different stages, your property acquisition drawing, you can identify, where you need it, because of great, filling. You want to be careful, if you got a big high fill and you track 15-foot centers, or if it's fairly short, you might be able to get that new track with 15-foot centers on the existing right-of-way. But if it's a big high fill or someplace where you're going to have to cut and put a ditch out there, you're going to have to draw. That's why you do that section and then do your initial planning to try to identify what acquisition you're going to need. What you can see here is here's the line, the grading line, which kind of identifies where you want to, where the limits of your construction are going to be. Generally speaking, everybody wants to buy properties kind of squared off. That's what we've done here. You know, we've got to get a little wider out here, a little narrow there, so you're not buying any more property that you want, but you're not trying to get it going, drop it back in here, and you know, it just makes it, you know, a lot cleaner to do something like this. But this is a clear identification of what property you're asking and why you're asking for it. Here's a situation where, you know, you're going to want to make exhibits to identify and try to how to make that clear. They wanted to have the drainage over on this side, but as you can see, that, you know, that got us into these trees. This guy used these trees to screen his property. He had his house up here, up in here. He used them to try to screen, you know, screen the railroad best that he could. So this gave a real clear indication of what they wanted to do. But we took another option, is possibly to put the ditch on the other side. His trees could stay where he had planned. We could, as long as we were doing this grading here, what that required is, you know, getting the water across here. So there was a little bit more piping work, but it solved dealing with this guy. And actually, you know, if the railroad could buy their property and just cut down the trees, that would be fine. But this guy had some, you know, real nice spruce trees and wanted to maintain them. So he was real reluctant to sell the property. But these detailed drawings were able to convince the railroad that, you know, they did have an option to go on the other side, and it helped the property, you know, the real estate guys from the railroad to get the, you know, acquire the property and get the right deal for it, and moved it on the other side. The property was cheaper at only a little bit more construction cost. Another location, that was where we ended up, this is that curve where we had to put the signals, but then we had to put, you know, the signal out here. Usually you would put it over on this side, you know, like I was saying, on the right side. But that was one, if we start putting signals in here, it was hard to drive down here to get here. So, and they wanted to put this out far enough so they can drive in here and they can still work it, but put the cantilever out here. They were able to see the signal. So them are some of the things that you want to take in. But the important thing is that here's a preliminary exhibit kind of showing. I think they might actually put it back over here because they thought they could get around it, because they thought getting over here and building a little retaining wall for that. This is the side that they wanted it on originally, but I think we came up with that. But when you show them an exhibit like this, you can say that trying to build this over there is difficult. As much as they didn't want it over here, you know, they wanted that better than having to build a retaining wall and having to cross the tracks to get to the maintenance. So you want to take all them things into account. Yeah, just quick on the, you know, so CAD standards. We want to, you know, does the railroad have any CAD standards? Base sheets. You want to get them set from the start so everybody's working on the same thing. That's a, you know, pretty much a no-brainer. You know, what coordinate system are you going to use? Is it some arbitrary one? Is it a state plane coordinates? That's usually a good one because now with all the GIS stuff from, a lot of counties, especially as they get closer to, you know, urban areas, you can utilize a lot of that information that's on the local state plane coordinates. I think partially it might have been for one of the railroads. It might have been for positive train control, but they did it on a different datum that was, you know, more conducive that it was a national datum, so you had to know where you were. But what it did was it provided them to have coordinate system on their whole railroad, the same coordinate system on their whole railroad, and that allowed the kind of to piece together everything. So you want to know what that is, making sure that you know what the scale of your drawings are, text size, what symbols are you going to be used, make sure you're on the right railroad, this guy likes it this way, they like it that way. We try to use Trans-Systems workspace and our details when the railroad isn't specific, but we also want to, a lot of times, select the CAD manager, not necessarily in the CAD manager thing, but who's going to be the one that everybody goes to make sure that it looks like one person is drawing, or producing the drawing. Making sure your naming conventions, the files, the drawings, even how you're going to call, do your call-outs, set borders, size of the, drawings. Are you going to do 50 scale, 100 scale? Prepare a drawing list so you have, a pen table for your drawing. Try to get all that information set up front. Now, quick, we're going to try to get into the, just some operating things that you have to consider. I think we're involved in trying to implement what the railroad has asked us to do. We want a siding here, but one of the things to try to get an understanding of is what are some of the operating characteristics of what we're trying to do, so we can help. That's one of the things that I like to try to do is, to understand don't do exactly what I don't want to be in a situation where I'm just doing what they're telling me to do, but trying to understand what they're trying to do so we can assist them. We can, a lot of times, especially now with a lot of younger folks on the railroad that are the ones that's sharing information, we can actually use our experience to assist them and determine that, but only if we understand what they're really trying to do. You're gonna, which way, we use the term, what are some of the restrictions? I think you might hear a trailing tonnage. That's basically what's the weight of the car behind the locomotives. What is the speed that you want to run? We want to run our trains at 70 miles an hour, so you're going to not want to put a lot of steep grades in there, because to maintain that 70 miles an hour, you're going to have a lot of extra power. Priority speeds. When you got coal trains that might be running a maximum of 45 miles an hour, and you got passenger trains that are running 79, how is that going to impact, the operation of that line? The faster trains are going to speed up, are going to catch the slower train. Well, one of the problems that you have is, a slower train, it's going to take a lot to slow it down, and then because of the tonnage, it's going to take a lot to get it started again. So if you put that coal train in the siding, you have an issue getting it started. There's a big schedule thing. It takes a lot longer to get over that railroad than if you get the train up to 45 miles an hour. It can keep it going that way across the entire subdivision. So a lot of times we're not going to know this information, but we want to get as good a handle on understanding that as we can. Is all the traffic in one direction, or is all the empties? It might be to a coal facility, for instance. They're hauling the coal into the power plant, or they're hauling it out of the mine. So which grade you have, if the train is empty, that's the way you want to have to go up the grade. If it's going, downhill, the tonnage isn't quite as much of a problem. So we want to understand that. How is the switching going to work? One of the BNSF lines, they call it the Transcon. It's their main line. They don't want any switching to occur on that. It's double track. They don't want any trains out there that don't need to be out there. Any train that's out there is going to cut into their capacity because they run so many trains on it. So they're not going to allow any switching. On a small branch line, they may allow switching out there. And what that's going to do is, may differentiate. You might need an extra runaround track on a siding, or, it depends on, someplace you're going to set out at an industry. how that's all going to be handled. So you're going to want to understand what are some of the restraints and ask that on the railroad or up to the railroad guy. Things that you're going to, maximum timetable speeds, it might, you're going to look in the timetable. It tells where, speed restrictions are. There might be different reasons for that. We want to, what train lengths, what are the sidings on that line. They usually don't want you to design anything that's going to be the most restrictive. So you find out what are the restrictions on that line and make sure that nothing you propose is going to make that worse. Another thing that's important is, the speed applies to the whole train. So if you make something slow, like, I can't figure out how to get this curve to be faster, than 30 miles an hour. Well, if the regular trains can run 60 miles an hour on that, the whole 2-mile long train, that 10,000-foot train, has to go, 30 miles an hour until the whole train goes around that curve. They have to start slowing down way early and have to, and so you're going to have a lot more delay than just figuring out what's the difference between 45 and 60 miles an hour. Switching impacts, you don't want to switch on a grade. So if you end up with a siding that's real, nice and flat, but it comes out onto the main line and the main line's at 1%, and you're going to have to do some switching there to where you have to go pushing cars up from a standing stop, uphill on a 1% grade is very difficult. So that might not be a great idea or a great location to put that siding. It may be where it's going to be an upgrade. So it's nice flat siding. It's a perfect place to put siding. But as soon as I start out, then I'm going to go up a steeper grade right outside of that switch. So when I'm, the mainline trains don't have any problems making up, it might be 0.6%. The mainline trains don't have any problem with ascending that grade. But because you stop on the siding and try to, start from there and moved up, or going up the hill, it takes a long time to get back up to their speed. You got to, the size of the turnouts will impact that, but then also the grade. You want to be taking all those things into account. Grade crossings, multiple tracks. Is it in a curve? You want to keep vertical curves out of crossings. Super elevation, the slant on the track. If you have multiple tracks that are on super elevation, here's a track that's tangent, a relatively flat crossing. If this was in a curve, and one of the reasons why you want to stay out of a curve, this outside rail will be higher. So you're going to come up here, and then you kind of, will flatten out, hit this one, and have to go up again, or all this whole plane has to be in a straight line, and you start coming up real high, and then have to get back down to the road. So you want to try to keep grade crossings, out of curves for that, one of them main reasons. Ruling grade, I mentioned that. That's usually the maximum grade on the existing subdivision. You want to kind of identify what that is. Usually you can find that in the timetable or on the track charts. If somebody's wanting you to do something, just you want to make sure that you're not making things worse. If it makes it worse, it might have to add an extra locomotive for every train that runs on that line than what they used to have, because they have to get up that thing that you just designed, and you don't want that to happen. Just kind of address, quickly, curve resistance. You'll often hear somebody ask that, compensated for curvature. So usually it's, if you want a 1 degree, it's a 3-degree curve, and you want a 1% compensated grade. So what that means is that you go through a 3-degree curve, you're going to need to add 0.04. It's like adding 0.04% of grade to it. So that's 0.12. And then so if you want a 1% compensated curve, you're going to subtract the 0.12, so that the actual grade can only be, would only be able to be 0.88% grade get a curve or to get a grade that would actually represent a 1% grade. So hopefully that's clear. I want to spend enough little time on the spirals and stuff here. Spirals, they're provided at the ends of curves, and connecting two compound curves. They're that transition from tangent to the curve, a smooth transition over time. It increase, the super elevation will increase. Super elevation is that, that cross slope that you put on the track, to try to smooth, to give you a smoother ride through the curve. Super elevation is, constant through the body of the curve. It increases from 0 to whatever, if you're going to have a 2 inches of super elevation, start at 0 at the tangent end of the spiral. When you hit the full curve, you'll be at 2 inches, and you gradually do that through the length of the curve. And then we're going to talk about a little bit here on calculating the length of spirals. One of the equations you want, equilibrium, that's kind of like, is that, where the train going around, basically just, there's a mathematical and a physics definition to it, but I kind of like to look at it as, if you go around there, you feel just like, like you hardly feel that, if you go around, like a curve on a highway, if you go around too far, you start leaning towards the, leaning like you're getting thrown out of the car, having a hard time staying in your seat. The equilibrium speed is where, when you go around that curve, it's super elevated at such an elevation that you can't even feel the curve. One of the reasons why they, like a Daytona 500, they bank that so fast that, so when they're going around the curve, they don't feel like they're going to flip out of the car, or the car is going to spin out. So they want that speed if you're going to run around at 200 miles an hour. We don't have to worry about that. But anyway, so the equation, the actual elevation, an underbalance is another thing. We'll talk about that in a second. Is defined by this equation. V squared is the speed in miles per hour squared. D is the degree of curve in degrees. The minimum is generally, depending on what railroad you're on, is 1/2 inch or 1 inch. If you're in a curve on the main line, you're going to want to have one of those. Reverse elevation is when the outside rail actually is lower than the inside rail, and it's easy for the train to, the wheels on the outside to lift up and actually derail the train. So one of the reasons for the minimum actual elevation is to prevent that from happening. You don't want to be going around a curve and have the outside rail be the low rail. So to prevent that from happening, you want to put at least a 1/2 inch or 1 inch, depending on which railroad that you're on. The maximum actual is somewhere between 4, maybe 5 inches, and that without approval from the chief engineer. So we want to take a look at that. Underbalance. This is a concept that it's a pretty simple concept, but sometimes it's very difficult to, one, explain and understand if you're not familiar. What underbalance is we got this equation up to the, so we come up with a super elevation, say that we go through this equation and we end up with 4 inch, it ends up with meaning, 4.12 inches of super elevation. You have, so 4.12, you're going to try to divide that up into actual elevation. So you might put 2 inches of actual elevation. So since with the equation, it's, we had 4.12, subtract off the 2 actual, leaves the underbalance is 2.12 then in that case. I have a couple examples. But what we usually use, the railroads are somewhere between 1 and 2 inches. Are usually each railroad has their track charts or curve charts that tell you what they prefer. You can figure out, 2-inch unbalanced, 1-inch unbalanced. One of the typically the maximum that you want in this underbalance is 3 inches. And what that means is that you are going to start feeling a little bit like you're going to go flying out of your seat when you go around that curve to the outside. You're going to get kind of thrown to the outside, just like in like an amusement ride. You're kind of pushed to the outside, and 3 inches for a lot of reasons is kind of identified as the maximum that you're going to want to encounter. Some of the other things is, you want to usually you try to balance the actual and the underbalance. And here's and when if you have two inches of underbalance, that's what you're trying to shoot for. You try to would go up to 2 inches of actual, 2 inches of unbalance, which give you the equilibrium of 4 inches, and then you can kind of work back through the equation that we use back here, and then figure out how fast you can go. And I'm going to figure out. This is one of them things where I probably need a little bit more time to share. But anyway, the length of spiral, here's an equation for that, is 1.63 times the E sub u, the unbalanced. Usually that for new construction. Sometimes the railroads may, this is something, not often used, but sometimes existing conditions, you could use that equation, would give you a little shorter spiral length. 62 times the E sub a. So all the railroads have their charts, so you're going to want to try to add that as a general rule. They have 44 inches per half an inch of super elevation is what the charts will actually provide you. But you want to take a look at each individual railroad is a little different. Minimum criteria, minimum length of spiral, they try to get a minimum of 100 feet. The body of the curve is 100. And the tangent between the curves is 100. It allows you to have a nice smooth curve that's actually maintainable, and it's criteria that generally you're going to want to follow. Some rules of thumb, that sometimes you might not be able to meet, but is certainly the target. So here's just one. Try to do a practical example. We got the speed is 40 miles an hour, and we got a 2.5-degree curve. So we go into our equation and add in here, we got 40 miles an hour, 2.5 degrees in decimals, comes up with his equilibrium elevation of 2.8 inches. So we've got the, E sub E is equal to E sub A plus 0. So, for freight, this probably should have had a, so that's 2.8. And then so what we're going to, we got our 2.8 inches of equilibrium elevation. The railroad's going to ask us that we want to do this for, 2-inch underbalance. So that ends up being, 0.8 inches of actual, the 0.08 plus the 2 gets you the 2.8. We are going to generally increase that to the higher 1/4 inch or 1/2 inch mark. So we're going to take the 0.8 to go to 1 inches of actual elevation. So then we'll plug that into our equation. We got 2.8. The underbalance is 2.8 times a 1 inch actual. So 1.8 times 40, which is the speed, gives me a spiral length of 117.36 feet. We're going to have 1 inch of actual elevation. Going through that equation, 62 times 1 gives me 62. So the spiral length that we're going to have is going to be the greater of either one of these numbers. So we use the 117.36. And so we rounded off to 125. Our railroad back in the day did everything in 39-foot increments because at that time that was something that started a long time before CWR, and all rail lengths were 39 feet long, so they did all their spiral lengths in 39 feet. So they would, it would be 117 is in 35 increments. The next one I think is 156. So one of them two would have been what they used. But usually, as a general rule, I usually try to round them up a little bit. The CSX has their own chart. You go right into the chart. So at 2.5 degrees at 40 miles an hour, they're going to say 1 1/4 inches. You have equilibrium of, the 2.8. So that gives you an underbalance of, 130. So the length of spiral and what we were doing before ends up with 77 feet. We calculated 117 feet before. They did this, I think the spiral is 31, 30, 30, with their, excuse me, I left out a little bit. It's 31, in this case, they have 31 feet for every ½ inch of super elevation. So if we have actuals is 1 1/4, so it ends up with 77. So the CSX is saying 77.5 is okay, where we calculated the other one at 117. Freight railroad's a little different. The underbalance is mainly for rider comfort. So if there's no passenger trains on there, this is what the CSX has chosen. It gives a shorter length of spiral. I think the longer length of spiral is better, because then if you decide at some point in the future you want to speed up things, you have some ability to do that, because the faster you go, the longer the spiral length needs to be. So I'm inclined to, if there's room, to make the spirals, reasonably as long as, is reasonable. That's a rounded up. Always you might want to round it up, where we had back in the last one, it was 125 feet. You may want to go to 150, which sometimes that might allow you to get up to 150 miles an hour or something, or 50 miles an hour instead of the 40 that we were using. And here's how you would do that. You have 40 miles an hour. You go to 2.5 degrees. This is what you normally are going to, each of the railroads going to have that. We came up with that 1 1/4 inch that we showed before. They want 1 1/2 inch unbalanced for speeds up to and including 60 miles an hour. So we got that. So we'll use this one, 31 feet, because we're going to do that up to 50 miles an hour. We were looking at 40. So that's how we got where we came up with, back in here where we came up with the 31 feet times the 1 1/4 divided that ½ inch. That's how we got up to 77. Each railroad has some a chart that's similar to this. You see that equilibrium equation here. That's, that'll be the same for all the railroads. How they apply it may be a little different, but each railroad will have this. Here's just an example: 5 inches of maximum super elevation on any curve. They're asked, in some of the other rules, each railroad has their own rules, and you want to take that into account. And I think we're getting close to the end here. There's a couple more slides. Vertical curves, just manual ride, manual grade change. The minimum vertical curve, I think we talked about that before, generally is thought to be 100 feet. I've heard another rule of thumb of 3 times the speed. So if you're going 60, it might be best to have a 200, 3 times 60 is 180. There's a case where I might try to put in a 200 foot vertical curve, try to get that transition as best as you can. You want to try to avoid rolling profiles. You want to keep that train stretched out. It operates a lot better. You don't want it, when it kind of bunches in together. The trains, you go over, a big hill. You're pulling the train, so you're pulling it up the hill, and then when you go over the top, the cars on the after they went over the hill, they can stretch out. They're going to, if you're going slow enough, they're going to try to catch up with the locomotive, so they start running in, and or the so you want to always try to get a situation where the whole train is going up a hill or down a hill as best that you can. Obviously you can't, but where the problem gets in is where you are in a situation where you're over two hills, two hills at the same time. So a lot of times you will try to make sure that you avoid that, particularly on the main line. It's not even a good idea in the yard unless you actually have to. Just always try to do that. Optimize the grade selection, for train handling and for grading costs. Sometimes you have to be steeper. I think they just had something on Palmetto where they had to exceed that because if they got the cut too deep, they're going to have to do some slope stabilization, which is going to cost them a significant amount of money. So they compromised on what they're doing to try to save some money, under being aware that the steeper grade may cause them engine burns or some other operating parameter problems. But the important thing was while they're going through that evaluation that those things are identified. And there's two different, the old version, the rate of change, grade coming up minus the grade, or the grade going down, or the second gradient minus the first gradient divided by the length of the curve, in stations. So if you have a 200-foot vertical curve, you'll divide the change in grade by 2. The criteria was on sags, you want to keep that number below 0.05, on crest 0.10. That was very restrictive in the railroads. Partially it was the transit community that wanted a better, that was the only one that was used in the industry, but the transit agencies try to push this newer one that handled, was more tied to the speed of the trains, and and the compromise at the freight railroads is in this factor, this A factor. They use 0.1 for freights and 0.6 for passenger. It usually provides a significantly shorter vertical curve, but check with the railroads, because a lot of times the railroads still prefer to use this one. They may, and I think this is just like I was mentioning, the length of the spiral. The longer vertical curve is probably better as well. It's a nice, more of a better transition grade. If you've got the room, make it a little longer than necessary. It's usually, usually better for you, gives you a better alignment, and usually railroad stuff, when you start cramping it down to the bare minimums, is usually when you start having troubles. But again, it's extremely important to always check with what the railroad wants to do. So some of the things, if there are any questions, I kind of went through some of that. Like I say, the super elevation and spiral length is really pretty easy. I think it's hard to explain, and sometimes it's hard to grasp until you've done it yourself once or twice. If we have a little more time, we have a few trials to work it out yourself. But if you have any questions, feel free to give me a holler, and be more than happy to spend a little bit more time talking through that, because it is, when you're out in the main line, that is one of the critical things that that you need to calculate and determine, because it is going to control, the speed of the train in the curve that you're going to provide. A lot of times the railroad's going to set that, so but you need to come up with a plan and know what their criteria is going to be, and making sure that you're not pressing that, and give them what they're needing at the speed that they want. So, sorry it took a little bit extra time, but if there's any questions, let me know, or give me a call afterwards, and I'd be more than happy to review anything with you. And I think Trevor will have, I think you can grab the the test off of the project-wise and take that and get that back to Trevor. Thank you for your time, and if you have any questions, don't hesitate to call. Thank you.
Yeah, the test, everybody, will be on TransU, so you can go ahead and do that this week as soon as you can. Just be sure to try to stay on top of it, and that's it. So thank you all for joining today, and we'll see you next week.
If after taking the test and you have anything, oh boy, can't remember even talking about it, and give me a holler, because I think we'll try to do that. For anybody that don't get enough right, we'll try to touch base with you anyway. So there certainly is no problem with doing that ahead of time. So thanks a lot, and we'll talk to you soon.